Welcome to Understand the Math. In this problem, we're asked to determine if the following matrices are diagonalizable. I'm going to start by telling you how you can determine if a matrix is diagonalizable. A matrix is going to be diagonalizable if either of the following are true. The first one says that our matrix has n distinct eigenvalues, and the second one says that the matrix has n linearly independent eigenvectors. So if a matrix has n distinct eigenvalues, it's diagonalizable. And if a matrix has n linearly independent eigenvectors, it is also diagonalizable. Let's go ahead and let's look at our first example. I'm going to write down that our matrix is equal to 4, 2, 0, minus 1. Notice that this matrix is an upper triangular matrix. There's a theorem that says that if a matrix is a triangular matrix, the eigenvalues are just the entries along the main diagonal. So we can write down that the eigenvalues of this matrix are 4 and negative 1. These are two distinct eigenvalues, so that tells us that our matrix is diagonalizable. Now let's look at our second matrix. This matrix is equal to 4, 3, 0, 4. It's also an upper triangular matrix, so the eigenvalues are the entries along the diagonal, and we can write down that lambda is equal to 4 and 4. In this matrix, we do not have two distinct eigenvalues, so our matrix may or may not be diagonalizable. What we're going to have to do is do a little bit more work and find out if we have n, or in this case, because it's a 2 by 2 matrix, if we have two linearly independent eigenvectors. What we're going to have to do is find the number of eigenvectors. To find the eigenvectors, we're going to take A minus lambda I, we're going to augment it with 0, and unfortunately, we're going to have to put this all the way down in reduced echelon form. Let's go ahead and let's do this. We're going to subtract our eigenvalue 4 off the main diagonal, so we get a 0, 3, 0, 0. So this is actually not bad at all. I'm going to look at this pivot, and let's go ahead and let's make that a 1. So our matrix is 0, 1, 0, 0, 0, 0. And there is our pivot. So this tells us, if we solve for this pivot, that we have x2 is equal to 0. And notice that our first column is missing a pivot, so that tells us that x1 is a free variable. So we have one free variable, so our x can be written as 0 times x1, and we can pull out the x1 and write this as 0, 1. So our goal was to find out the number of eigenvectors that we have, and we ended up with one linearly independent eigenvector. But for our matrix to be diagonalizable, we needed 2. So we can say that our matrix is not diagonalizable. Before we end, I want to make one note. Notice that we had one free variable. The number of free variables is going to be equal to the number of eigenvectors. So up here, when we found that we had a free variable and we only had one, we actually could have stopped and we didn't need to really find x, because just having one free variable will tell us that we just had one eigenvector and not two, so our matrix was not diagonalizable.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.